Okay, recording in progress. So I'd like to welcome everybody to today's PRIISM seminar. We're delighted to be joined by Dr. Jessica Godwin, and Jessica is a statistical demographer and the training director for the Center for Studies in Demography and Ecology at the University of Washington. Their broad research interests include demographic methods, Bayesian spatiotemporal methods, survey statistics, and the places where all of those things overlap. Jessica received their PhD from the Department of Statistics at the University of Washington and is a former Center for Studies in Demography and Ecology trainee and fellow. And so with that, I'll turn it over to you, Jessica. Thanks so much for joining us. We're delighted to have you. Feel free to kick things off.
I'm really happy to be here. And I know that Twitter is dying, but I do have to say that I think the reason that I'm here is because Daphne and I found each other on Twitter, academic Twitter, a couple years ago. So if Twitter doesn't die, I highly recommend, getting involved in those kind of things. You won't be surprised who you can meet. So, right, is there a chat? Okay. Can you all see my slides? We're all good? Okay. So the title of my talk is Subnational Estimation of Period Child Mortality in a Low and Middle Income Countries Context. And so before we jump into what all of that means, I'm going to kind of give you some background on some of the pieces in that title. But first, I'm obligated to acknowledge several grants that have funded this work over time. And just to give a little bit of background about myself, I was a PhD student in statistics at UW, hence this logo here. CSDE is the Demography and Population Center at UW, where I was trained in demography, which I didn't know what that was or anything about before I showed up at UW. And before that, I did my bachelor's in actuarial science and my master's in stats at Auburn University in Alabama. And as I was searching, I realized I didn't have a logo on my computer, but I did have this picture of Charles Barkley. So the patron saint of Auburn, if you will. So I took kind of a winding road to end up in statistics. I had no idea what I wanted to do. I didn't know what demography was, but I'm glad I found it. So we're going to start with a little bit of background on demography, and then sort of the motivation for why child mortality estimation is important, why subnational child mortality is important. And then I'm going to kind of go through a lot of background. And one thing I kind of want to make clear here is I'm showing you one little part of at this point, basically a decade-long research project that is still ongoing. So I'll kind of give you the background on where it has been, talk about the portion that made it into my dissertation, and where our lab is going in the future. So does anyone know what demography is? All right, I see a hand, Robert.
Statistical and mathematical study of population.
Yeah, there we go. So, I'm sure every time people ask me this, then I ask them if they know what demographics are, and then they are like, oh, okay. But the crux of demography really is this balancing equation, where if we know the population at time t, and we want to know the population size for some population at time t, we want to know the population size at time t plus 1. It's mathematically true that that's the number of births minus the number of deaths, plus the in-migrants minus the out-migrants. So demography really, formal demography refers to studying, estimating, developing methods for or projecting anything in this balancing equation. Some of the components are easier to measure than others. And then I would say the other really important thing about demography is not just these singular components of fertility, mortality, migration, but how they affect one another, and how they work together to create population dynamics over time. I would say demographers are also very well known for then breaking this all down into subgroups of the population, usually age, sex, race, ethnicity. But the why is a little bit different, I think. So of course, in terms of needing to know the size of a population for planning, for schools, for pensions, that's all there. But a lot of demography really is thinking about, okay, if mortality is high, how can we lower that, right? There is some amount of responsiveness to not just wanting to describe a population, but once we've described it, what do we do with the information that we've learned? And a lot of that really falls into social demography. Why do we see differences between different populations and their mortality rates and their fertility rates and their patterns of migration? And then there's a lot of people in the demography world that do really cool stuff, like pore over handwritten records of populations from hundreds of years ago to understand what those populations were like. And that all kind of falls under the umbrella of historical demography. So what we're going to be talking about today, I think really falls in these first two, perhaps three, but definitely the first two bullet points. So there's two main ways demographers like to measure age-specific mortality, which is what we're going to be moving toward as children are a specific age category. And just in case people aren't familiar with notation or maybe work with one of these things more than the other, I think as statisticians, we tend to find ourselves drawn to probabilities over rates, but people can measure mortality in rates, which is the number of deaths over exposure. If any of you are more in the epidemiology realm, you probably work with rates all the time. And then probabilities, which we all know we like as statisticians because we have distributions that describe the way they behave very well, would be actually measuring the number of deaths divided by the number of people who could have died. So when we talk about exposure, we're talking about the amount of time people were alive. We might think about the number of person years or person months lived as the denominator. The other thing that demographers are really, really particular about is, besides are you measuring a rate or a probability, is are you measuring cohort or period mortality? So cohort mortality is sort of the easiest to explain, and it's when you want to describe mortality experience, and if we're doing age-specific mortality, the mortality experience between in an age range X to X plus N of a birth cohort. And often birth cohorts are defined by calendar year or 5-year calendar period in demography. Period mortality, on the other hand, is probably what most people think about when they see a number or are asking, what is the risk of death before your 5th birthday in a place right now or in the past? And it's really referring to the mortality experience of individuals in that age range during a specific calendar time. So if I want to know like the child mortality in the US in 2020, that is a period mortality measure. If I want to know the infant mortality rate of children born in 2020, that is a cohort measure. And the reason those are different is because if we think just about that first year of life, who dies between 0 and 1 in a calendar year, say 2020, some of those kids, babies, would have been born in 2020, but some of them would have been born in 2019, right? If you're born anytime after January 1st, right, you could technically die before your 1st birthday in the next calendar year. So it's really taking account of these multiple cohorts contributing to one time period's mortality. And then the other interesting thing about period mortality that I think demographers think a lot about, but it may not be obvious or intuitive at first, is while I think we all want to know about period measures more often, cohort measures are usually reserved for things like lead exposure or smoking, things that really did affect a different birth cohort and the way they moved through those ages differently than other birth cohorts. If we want to do age-specific mortality for a population for the year 2020, which has been the subject of many, many studies, we all know, and we look at the whole age range, there's no one individual in that population who ever experienced that age-specific mortality structure, right? No one person was in the age range 0 to 5 and 5 to 10 and 10 to 15 and 85 to 100 in one 5-year calendar period or 1 year. And so even though it is the snapshot of a population's mortality in time, it's kind of interesting because it doesn't really describe anyone's lived experience with mortality throughout the course of their life. Okay, so why child mortality and not something else? Outside of the oldest ages, child mortality in any population is the next highest age range or risk of mortality. And where child mortality remains high and has remained high in the past half century or so, those are often due to preventable deaths like diarrhea is one of the #1 causes of child death in low and middle income countries today. So having access to clean water or even just access to healthcare, and then dying from diseases that other parts of the world have already done public health interventions like vaccination that really cover big swaths of the population. So things we know as a planet how to prevent, but there are populations where those deaths are still not prevented. And this is distinct from things like maybe SIDS or there's some proportion of babies that are just going to die even with the best healthcare, right? So we're really thinking about this, what we think about like excess death or the preventable death. And because of that, it's often used actually, well, for 2 reasons. Because high mortality in this day and age is usually an indicator of the overall health of a population because it is representing this still existence of preventable deaths. It also is one of the few ages where a lot of effort is concentrated in measuring mortality. So it's often used as an indicator in demographic circles for a population's overall health, because if it's high, it might be indicative of other things that are going to increase mortality at other ages. And also it's the age group we have the most information about. And so the common indicators that demographers use for child mortality are the under 5 mortality rate, which we'll talk about today. This is often referred to in that demographic notation I showed you a moment ago as 5Q0, the probability of dying before your 5th birthday, given that you survived to your 0th birthday. The infant mortality rate, which is the mortality in the 1st year of life, and then the neonatal mortality rate, which is sorry for my bad LaTeX typesetting there, probability of death within the 1st month of life. And so the reason I brought up rates and probabilities a moment ago is that these are all called rates, but actually they are probabilities. I don't know why demographers did this. Someone did this like 100 years ago. And even though they're big sticklers on whether you're estimating a rate or a probability, somehow the term for the biggest probability measures used in demography include the word rate. So from here on out, if I refer to U5 and MAR, I'm talking about the under 5 mortality rate. As I said, they're probabilities, not rates. So why child mortality in low and middle income countries? Why subnational mortality? Well, in the 90s, the UN developed the Millennium Development Goals, and there are a whole list of goals. That sort of period of goals ended in 2015 and has been replaced by the more recent Sustainable Development Goals. But both of these sets of goals are big, broad goals for the entire globe on a whole different, a whole array of categories of things. Some of them aren't even related to mortality. Some of them are related to health. Some of them are related to climate and climate impacts, but always reducing child mortality in these areas where we know that a lot of child mortality that's high is preventable has been one of the predominant goals. And so there is some aspect of why we do what we do is for the sake of monitoring progress toward these specific goals. The most recent SDGs, which we're under now, call for an end to preventable deaths and a reduction of NMR to 12 deaths per live birth, 1,000 live births, and U5MR to less than or equal to 25 deaths per 1,000 live births. And then there's also a specific call in the SDGs, though pursuit of subnational estimation was already happening, for understanding how variability across all different subgroups in a population, including geographic location. So how is child mortality measured so that we can understand a country or population's level and trends and progress toward these goals? There's three main sources of data. One is vital registration, and so that's probably the one that most of you are familiar with. A state issues a birth certificate and a death certificate, and those are in some population register. And with proper access, you can know, for the most part, the number of births and the number of deaths, and you can count this all very well, with the exception that maybe some people aren't covered by vital registration. And the issue is in that in most low and middle income countries, the vital registration system either doesn't really exist at all, or if it does, it does not cover the population anywhere completely or close to completely. And a lot of that is actually due to the fact that in rural areas and low and middle income countries, a lot of people do not give births in health facilities. That's changing and has been changing over time, but you can imagine that if you're not even going to a health facility to give birth, you're not going to make some big journey and spend money to go buy a certificate that says, hey, I have a child. So that is the main source of data in high income countries, but it's really not usable in a lot of low and middle income countries. So starting in the 80s and maybe a little bit before with summary birth history, other kinds of data were started to be collected in these countries to monitor demographic measures and also health in general. And so we're going to talk mainly about full birth histories throughout this talk, but summary birth histories will come up a little bit. So full birth histories are collected via household surveys. The biggest one of those that I'll talk about a lot today is the demographic and health surveys, and those are funded by USAID. And USAID works in conjunction with national statistical organizations to conduct huge countrywide household surveys, usually every 5 years. And this has been happening since like the mid 80s. And when they interview a woman, they ask for the birth and death date of all of the children they've had and the death dates of the children who died. So we get time of birth, time of death with maybe some measurement error in there, but we really get a full survival information on survival up to the time of survey. Summary birth histories are often collected via censuses, which means they cover a much bigger part of the population, but we really lose the information that we as statisticians kind of care about. We get to know the number of children they've had and the number who have died, but we don't get any of that timing or exposure or anything that can really be used in a survival analysis, right? So demographers have used summary birth histories. They love it. They have methods to deal with it. I would say most people I know who sort of work in statistical demography and care about uncertainty prefer to work with full birth histories. So these MDGs and SDGs, this is a graph of global progress toward that. And here, the top left, this is the globe. Here is sub-Saharan Africa, and this is Southern Asia, Southern and Eastern Asia. And so what's going on here on the y-axis, we have proportions, and the colors are representing the number of countries in that group that fall into these buckets in terms of number of deaths per 1,000 live births before age 5. So this dashed line is the end of the MDGs. And we, as I told you, the new goal is to get into the yellow category by 2030. And so you can see for the world as a whole, there has been general progress over time. This yellow bucket is growing, right? And the other high mortality buckets, which you can see the ranges here. I mean, that's like an order of magnitude larger, right? 10 times larger. But when we focus on the places with the highest mortality, which there's only 11 countries in Southern Asia, according to the UN group, which is why there's, some kind of wonky patterns here. But for Sub-Saharan Africa and Asia, we see that there's a lot less yellow in general, and particularly in Sub-Saharan Africa, many more countries at, in the 1990, more than 20% of countries were losing, what is that? At least 200 children for every 1,000 live births. That's a 20% mortality rate. So, and at the MDGs, you can see that there's been no change in the yellow bucket for Sub-Saharan Africa, and just a little bit adding a few countries here. I note in Sub-Saharan Africa, this ART scale up, because you can kind of see there's not a lot of change here, and then all of a sudden we see a big growth. And that ART refers to antiretroviral therapy. And so a big part of child mortality in Sub-Saharan Africa for a long time was due to mother-to-child transmission of HIV/AIDS in countries with with generalized epidemics. And so once ART, even though it existed in high-income countries, once it was finally, there was a global initiative in 2006 to get this distributed throughout Sub-Saharan Africa, we really see these improvements. But we still do not really see any improvement in this lowest mortality bucket. So this is kind of covering what I've already told you before in words, but child mortality is still high, even though in a lot of places there's been a ton of improvement. We can't really use VR data in most low and middle income countries, so we have to rely on full birth history data, maybe summary birth history data. For national estimation, the national estimates of child mortality, the UN Interagency Group for Mortality Estimation, which I will mention a lot, IGME, they do this and they combine all of these different types of data where available for any country. DHS itself, the survey administration, the Demographic and Health Surveys, they produce national estimates of child mortality in the year of the survey that they conduct. And then here at UW, we also have the Institute for Health Metrics and Evaluation, and they're also another big body that makes official estimates of child mortality. Subnationally, however, IHME had done this originally, and then IGME came to us. And so my advisor, John Wakefield, and our sort of big sprawling group over the past decade worked closely with developing methods and finally making official estimates at the subnational level for child mortality with UN IGME. So before we go on, what do I mean by subnational? And that could mean any number of things, but in demography and in these circles, we're typically talking about administrative divisions of a nation. So in the US, or in any country, admin 0 is the country itself. In the US, admin 1 would be like US states, and admin 2 would be like counties. So here I have a map of Kenya on the left and Malawi on the right, where the color, the lines are representing the admin 2 areas and the colors represent the admin 1 areas they lie within. So at the admin 1 level, you can see we're not really dividing the country up very much. And at the admin 2 level, we're getting much more fine. This can, range all over Africa. For instance, in Nigeria, they have like 700 admin 2 areas. So the problem and the scale of the problem in terms of being able to have sufficient data to make estimates at the admin 2 level varies by country. So let's talk about the data we do have and what we use to do subnational estimation. So we have these household surveys, and like I said, they've been around forever and their purpose, though we can talk about maybe some critical or ethical issues with them, has been to monitor population health and demographics over time. And they've been doing that in 90 countries, starting at different points, but going back to the 80s. And the sampling frame they use comes from a country's census more often than not. So the last census they had. I'm really sorry about that. And they call their primary sampling units, or like, so the first level of sampling, usually called enumeration areas. These are analogous to US like census tracts, okay? So they take all of the census tracts or enumeration areas from the last census, and then they stratify those by whether they're urban or rural in designation. And that definition is really ambiguous. It can change across countries, and it can change within a country over time between censuses. And then usually almost all, this isn't true of every single DHS, but most of them then stratify by what admin one area the enumeration area is. I'm really sorry, I thought I put my notifications off. We're in the process of house hunting, so I'm getting a lot of messages. I'm really sorry. Go away. Okay, maybe I should just ignore it. So they have this big list of census tracts, then they want to sample, and they sample usually with probability proportional to size. So, and the reason for doing this, if you're not really familiar with survey sampling, you can imagine if we want to sample, say, cities in the US, and you just put them all in a big hat and sample at random, what if you just don't get LA, New York, Chicago? Like, what if you miss all the big cities? Then all of a sudden you have sampled 1,000 cities, but you're missing large swaths of the population. So they sample these census tracts with proportion to their size by population. And then once they've sampled those, and these can either be like urban blocks or rural villages, they send out a team to enumerate all of the households in that area. And then they do a systematic sampling where they have a map of all the houses, and they take like the 7th house, the 14th house, and so on. And then within those households, all women aged 15 to 49 who slept in the house the night before are eligible to be interviewed. And these interviews last like 9 hours. So we're talking about full birth histories, but they collect so many things, including blood tests with consent, a ton of different things, information on what's in the house. Do they have running water? What kind of toilets do they have? A million things. You might be worried about non-response, but it might surprise you to know that non-response in these surveys is very low. And if you work with surveys in high-income countries, it will kind of blow your mind that I would say the highest non-response I've seen in general is maybe like 80%. And that's usually for the half of these households where they try to interview men, and then those men are often gone for months on end doing seasonal labor migration. But amongst the women's survey, it's usually less than 10% of women refuse the survey. And so they collect the full birth history for each child. They ask them the birth date of each of their children. And there's a lot that goes into that. Like I said, if there's not a birth certificate, knowing the exact month and date, especially going way back in time, may not be possible. So the interviewers will use things like the season, the harvest, trying to kind of narrow down where it might have been. And then for the death date too, there's usually a little bit of imputation or trying to understand exactly when. So we have to account for this stratification, and we should be accounting for the whole sampling scheme. For those of you who have done survey statistics, it really matters. But I think most important, with stratification, if we don't account for that, we can get biased estimates at the subnational level, right? We have this urban-rural stratification that affects every admin area. And it's historically been the case that rural mortality is much higher than urban mortality, though there's starting to be evidence of maybe a flip there. And then this is like, one of the worst statistical sins we could ever commit. We might overestimate our standard errors. We never want to do that, right? It's always kind of the other way around, where we might underestimate them and be like lying, but we would sort of be missing some free lunch if we don't account for our stratification. And the consequences of not accounting for this worsen as the relationship between strata and mortality increases. So if there is a big variety in the level of child mortality across admin or admin 2 areas, and particularly between urban and rural areas, we could be missing out on that. Not accounting for the clustering does the opposite. We could be underestimating our standard errors. And this also worsens as the relationship between children in the same census tract and within the same household, their mortality is more dependent or correlated or related with one another. So for those of you who have not done survey statistics before, I'm going to talk a little bit now about how we might account for the complex sampling design in analysis of data from a survey. So if you've had a lot of stats classes, which I think most of you have, most of those are going to fall under this model-based methods bullet. We're thinking about an infinite population, a superpopulation, or this idea of like, what if we reran history from the beginning over and over again? How many children would die, right? There's someone or something up there flipping our binomial coin every time a child is born to see if it will die with some, probability. But often survey statistics are approached from what's called a design-based perspective, where we're really thinking about a population that we're surveying or sampling from as a finite population. So this is more like a hypergeometric distribution. We're sampling out of an urn without replacement. And what's random when we go to analyze this is not our outcome of interest. It's not whether or not a child died or whether or not someone has a particular disease. Those are fixed. Those are known things. What's random is whether or not they end up in my survey. And the hypothetical experiment that would be repeated over and over again is sampling from the urn again, filling it all back up, resampling, okay, how many do I estimate? So to use design-based methods means to account for the stratification, the way we sample, all of that, using sampling weights, which are the reciprocal of the probability that an individual shows up in our sample. So in this way, someone who is really likely to be sampled has a high probability, gets a lower weight than someone who is very unlikely to be sampled. And in absence of non-response, we can often think about those weights as representing like the number of people in the population that person's information represents. And so this all really works in sums of squares, like if we're estimating variances, but we are estimating sums of squares within strata. So we're subtracting from the strata mean, and then we're thinking about variability and variance from the perspective of a cluster. The problem is, I think a lot of people who work with surveys would prefer to use design-based methods all the time. There's a concept of design unbiased, which basically means as your sample grows, you get the population truth back. But when sample sizes are small, the variance estimates are very large. So that's a problem, and that's often when people turn to model-based methods, or if they're not given these sampling weights or the appropriate information to calculate them. And in that case, we tend to put fixed effects in a model, just like your regular, whatever linear model, logistic model, whatever you're doing, fixed effects for your strata, and random effects to sop up your within cluster variability. So we're kind of here at the meeting of a lot of different statistical areas. So one of them is survey statistics. Another one, when we're thinking about subnational estimation, is spatial statistics, and there's a decision to be made about whether we treat space as continuous or as discrete. And so everything that I have here with a name is either directly part of our group of work or things we built directly off of. And in different applications, there's a lot of other people who work in discrete space or continuous space, but these citations are particularly around mortality and child mortality. IHME takes a continuous spatial approach. So they're like I said before, sort of the only other people doing this on a large scale. And we have looked at that, but ultimately we have decided to take a discrete spatial route at this admin 1 or admin 2 level. For all of our estimation. And so because we take a discrete level, the other sort of third branch of statistics that's really coming here is called small area estimation. What happens when you want to estimate information for subgroups of a population? The small in small area is not usually referring to geographic area and their size, but the number of people or subjects or observation units in whatever that subgroup is. So it could be sex or age or race, ethnicity. In our case, it is administrative divisions. And it's important to bring this back to survey statistics that often when we're talking about small area estimation, these small areas are usually not our strata, right? If they were our strata in a survey, someone who was in charge of spending a lot of money and doing the survey design decided how many people we needed to sample within our strata to estimate anything about our outcome for our strata. So we have a large sample size. Usually small area estimation is referring to subgroups within the population where the design for collecting data did not take into account power to detect whatever you need to detect within that population. So there's sort of two branches here too. There's area level methods, which involve estimating for our administrative divisions or our small areas, estimating something for an area with only information from that area. So if I want to estimate child mortality in Washington, I'm not going to use information from Oregon or Idaho to do it. Unit level methods, on the other hand, use all the information to some degree to help inform estimation of at the area or the small area level. And so our work as a group, and my work in particular, has straddled both of these, and I'll talk a little bit more about when and why in a minute. So up until the point of what I'm about to show you, back, gosh, almost a decade ago, John started working on this with another student, Lena Mercer, and they first did admin 1 only estimation using these full birth history data from the DHS. And then I was part of a big project where we did this at the admin 1 level for 35 countries, which was a big undertaking. But if you remember when I described the sampling procedure for DHS to you, admin 1 are usually strata in the DHS. So there is a decent amount of information within each admin 1 area that allows us to do this sort of area level estimation. But at the admin 2 level, which is really what countries are wanting, there's a lot of variability within these admin 1 levels, and they want to know, where do we put interventions? Where do we spend our money? Where do we really need to focus on preventing child death? And so we started by looking at Kenya and Malawi because they had recent DHS surveys that were actually stratified at that level. And we were able to produce admin 2 methods in the same way that Lena had for Tanzania and that we all had as a group for 35 countries. And actually the first chapter of my dissertation was trying to also bring in that summary birth history data that I said we're not going to talk about a lot, thinking it might help. And it didn't really help. Like, it was a lot of statistical work for very little payoff. And we didn't think it would work for countries that didn't have enough, didn't have stratification at the admin 2 level or enough information at the admin 2 level. And so this is kind of a picture of how it didn't work. Here's Nairobi from Kenya. Lilongwe is an admin 2 area in Malawi. And these big circles are those summary birth history data. The big lines are the full birth history data. And so the summary birth history data, if you recall, if you remember, I told you they usually come from censuses. So we get a ton of information, but the way we analyze it is, I mean, it's hard to know. We don't know when those children were born. We don't know when they died. We just know how many. So here, the size of the dot represents the uncertainty, or sorry, the precision attached to that estimate. So we know something very precisely from the census, but it's biased, whatever it is. We don't know the statistical properties. We can't do proper survival analysis. And in Malawi, those censuses kind of lined up with all of the household surveys, and it did get us better confidence intervals or Bayesian predictive intervals for our estimates, which is what we wanted. But in Nairobi and in everywhere in Kenya, it was kind of the opposite. The censuses were all over the place. They conflicted with the surveys, which we know how to model those in an unbiased way, and they didn't really help. So this is sort of the pipeline that I've made that kind of describes our lab's work toward the estimates that we published with the UN in 2020. And we start with only DHS full birth histories. We've abandoned trying to use summary birth history for now. We need from each of those the geographic location of the clusters. If you recall, I told you that often stratification happens at one level up from admin 2, where we really want to be making our estimates for. So in the survey file, we know the admin 1 area every child lives in, but we don't know where they live in the admin 2 sense. So we can only use the surveys that provide cluster locations for the sampled enumeration areas. And then we usually get these from a different place, but we need shape files that tell us what the admin 2 areas are. And then we process our birth histories for a survival analysis. We have birth dates and death dates, and we want to expand that into survival data for 1 month of life that every child starts. So if a child lives till their 5th birthday, they get 60 rows of data in our data frame. If they die in their first month of life, they just get 1 row. And here this is a schematic sort of describing all of the things I just covered. What kind of survey statistics approach are we taking? What kind of spatial approach are we taking? And what kind of small area approach are we taking? And so if we're going to use our survey weights, and this would be direct estimation and design-based estimation. And then we often, this Mercer model, the Tanzania, the 35 countries I told you about, we take these design-based estimates, and then we do Bayesian spatiotemporal smoothing of the area level estimates to get more precision. But when we found that that wasn't going to work at the admin 2 level, that the estimates that we'd be feeding in were just way too uncertain, we kind of had to go back and rethink, okay, this is what we would like to do if we have enough data, but we don't. So what are we going to do? And that led us to this unit level model where instead of doing the design-based survey weighted estimate, taking those estimates and then smoothing them across space and time, we fit our model for child mortality and do our space-time smoothing all in one step of model estimation. So we're doing a unit level model-based approach and not using our survey weights. Okay, so now for the real statistics. This is a ton of background, and now we'll have equations and stuff. So for each individual, child K, born at some time T star, and was either died or observed alive at age A star, we only have information from the DHS on the monthly scale. So time is continuous, right? But any child who's born with any time within a calendar month, we're going to assign them to, say they're born at the beginning of the month. And if they die any time between a month of life, whether it's the first day of their 2nd month of life or the last day of their 2nd month of life, we're going to assign that month of life as their death. So for each individual, they get a Y and an N, and then we aggregate all of that up to the enumeration area. So we have age in months and M. I indicates either admin 1 area or admin 2 area. C indicates cluster. That's the enumeration area or sampled village or urban block. T is calendar year, and S is the survey from which we're pulling this information. So for any individual, since these full birth histories go back in time, right? We interview all women 15 to 49, and they give us their whole life's fertility history. Multiple surveys contribute to multiple time periods in the past. So we know whether the child dies in any 1 month. And then if they begin that month alive, we give them 1 age month, in a binomial sense. They get to flip that coin. But the Y can only ever be 1 in one of their Ys, right? They have a flip for every month of life they start alive. But at most, the last Y can be 1. It's very common in demography to acknowledge the fact that mortality changes rapidly over the first 5 years or 6 months of life, the risk of mortality. It's highest in the first month of life, hence why neonatal mortality is of interest. It's highest in the first year after that, and then it really falls off. So we have decided to make assumptions of constant mortality between a few age bands. We separate out the first month of life, the next 11 months, and then the subsequent 4 years, and some aspects of our modeling for our temporal smoothing. This is for our mean. We get a mean risk of mortality in each of these age bands, and then we smooth the temporal trend according to these age bands. So we allow the temporal trend to change within the first month of life, the subsequent next 11 months, and then all years after that get another temporal trend. So to account for the dependence within clusters, right? You may have taken a general linear models, general linear mixed models. You might think, okay, we'll just put in an IID term for cluster. That's sort of what we're all taught in our first class. Well, we don't have a lot of data and we have a lot of clusters. And we could do it for the cluster level, but what about the household level? All right, we very slowly are unable to estimate all of these things, especially when we're wanting to do the smoothing across time and space. So after a lot of different models, we actually settled on using a beta binomial model and allowing that dispersion parameter from the beta binomial model to do what a random effect might do otherwise, to really account for that dependence within clusters of mortality. So, and the likelihood with the binomial, our mean model looks like this. We have a mean log odds of death in 1 month of life. If you recall this demographic notation, M here is the month of life that a child would start, and we're going to estimate the probability of dying within that month for every month from 0 to 60 months. And then for those 6 age bands, if a month is in whatever one of those 6 age bands, there's a fixed mean. But then we have an age time effect for those broader age bands, because we really just did not have enough information in some countries to estimate a time trend for each of those, the 4 years 2 through 5 on their own. And part of that is also because mortality becomes much more rare at that age, right? Even though it's not just sample size, it's also the amount of information we have due to the rarity of the binomial event. So we have an IID temporal effect for each year, and then we have a random walk to in time across years for each of those broader age bands. And we kind of think of this IID effect as sopping up sort of, I don't know, if something strange happened in 1 year or some, residual variability, and we don't actually include that term when we then go to make our estimates. In space, we use a BYM2 model, if you're familiar with that, but basically it's assuming that for an area in the prior, that an area's outcome or mean mortality is related to that of each of its contiguous neighbors. So if there's enough information in the data that the area is very different from its neighbors, the posterior will pick that up, but a priori, we're assuming some sort of spatial smoothing there. We have space-time effects. So we have a space-time interaction effect that also has dependency across time, like a random walk 2, and across space, like the ICAR or the BSAG-York-Mollier. And we also have a random area slope in time. And then we have bias terms here. So one of these is because if we have multiple surveys, we need to account for the fact that they're all estimating the same thing, but we have other sources. And then I already mentioned the HIV/AIDS epidemic in a lot of these countries, but when you think about our sampling frame, if a woman died from HIV/AIDS long ago and would have otherwise been alive and eligible to be surveyed, they can't be surveyed, right? It's non-response in the sense that they cannot be a part of the sampling frame. And we know due to the mother-to-child transmission of HIV/AIDS that this is going to bias our outcome, because if the mother is missing, the children were probably more likely to have died as well. So this is we use someone else's method, but it's basically putting in a log offset for the ratio of mothers we think we missed due to HIV/AIDS. Any questions? I know this is kind of a lot to just go straight into a big model. Any clarifying questions before we move on?
Just throwing you a time check.
Okay, cool. Thanks. All right. So I will speed up. Thank you, Dana. You might notice that I spent a lot of time talking about stratification. We don't account for stratification here because we realize that we need to know the fraction of children age 0 to 5 in urban and rural areas over time. We would need to make an estimate of urban mortality and rural mortality and combine those. So this is just an example of how research works and takes a long time. We wanted to do this, and all of a sudden we're like, oh, that's another research project. Someone has since sorted that out. So once we fit that model on the monthly scale, we need to get the U5MR, the probability of death before age 5. And we just use rules of probability, assuming conditional independence of those monthly mortality rates across time. And then we benchmark the national estimate to the IGME national estimate. They get to use a lot more data in their national estimates. So we use that so that we have some consistency at the national level. So one thing I'm going to speed through real quick that distinguishes our, there's a lot of things that distinguish our methods from IHMEs. We use discrete space. I went through all of these different things, but one is that we model each country specifically. So this round of estimates, we did 22 countries, and there's a link in here. You can go to childmortality.org and see all of our estimates. But IHME takes sort of a regional approach, and we think that there's something valuable in paying attention to each country specifically. And so one of those is Myanmar, where they had a big cyclone in 2008. And it only affected this little portion of the country. On the right-hand side, we have the population distribution. And so you can see that the most populous part of the country is here, but there's still some amount of population where this was affected. I'm going to kind of skip through a little bit of the details, but we realized we needed to make some sort of crisis adjustment because that crisis was missed by the surveys. And here on the left, we have the comparison of our estimates after doing this crisis adjustment. And we did it at the subnational level, knowing this crisis only affected a small portion of the country's children. IHME, on the other hand, distributes the known deaths to children from the crisis evenly across the whole country according to its population distribution. And you can see that I mean, it's just clearly not correct in that year. We know we should have an increase in mortality here. And at the admin 2 level, this discrepancy looks even more different. And so while we have this pipeline that's reproducible and we do basically the same method for every country, we really do take care to adjust each country's estimates according to their needs and the lived experience there. And I kind of speed through these so we can get through time. So that was a big overview of the method used, but we did that method for 22 countries, and those results are available at childmortality.org. They're completely replicable if you have sufficient computing power. For some of these countries, the models took days to run. But there's a lot of ongoing and future work, and we're actually in the current process of doing our updated estimates using a lot of this new research. So another student of John's worked on the stratification issue, so we can finally estimate the proportion of urban-rural for children, and we can actually account for urban-rural stratification in this round of estimation. One issue, though, is that that definition of urban-rural changes with each census. So we have a bargain to make. Do we use all of the data and not account for urban-rural stratification? or do we use a smaller subset of surveys? We've also had a student, Taylor Okanek, who improved our benchmarking to be more of a soft benchmarking, acknowledging the fact that the national estimates we're benchmarking to are also estimates. And then I'm working on some really interesting stuff to me that is really, you know, if you start in demography corner and walk to where we are, if you start in statistics corner and walk to where we are, how do those different models overlap, and how do different big agency groups use the same data and end up with different numbers at the end of the day? Yeah, that's it. Sorry, I had to rush there at the end. Any questions?
Thank you so much. That was super interesting, and I know I learned a lot. So yeah, if there are any questions, we'll take time for 1 or 2 of them. So feel free to unmute or put a question in the chat. Yes, Robert.
Hi, thanks so much for the talk. And I have just a quick question, and it may just be that I missed the detail. I'm curious, in your model, it sounded like essentially your spatial autoregressive component was a sort of nearest neighbor sort of thing. I'm curious if you thought about a sort of more sort of canonical spatial autoregressive model that sort of uses spatial dependence and some measure of distance and decay.
Yeah, so that really gets back to that. Are we going to treat space as continuous, or are we going to treat it as discrete? And so if we treat it as continuous, we actually have a student who's worked on, like, in this context of sampling, did this giant survey, like redoing all the sampling and then thinking in the context, this specific context of these big samples, what's the difference in continuous and discrete space? And it turns out in a lot of cases, there's not a huge difference in the actual outcomes of estimates we get, except that the continuous spatial models and like a typical Matern prior, it just takes so much longer to compute. IHME do continuous space, but they do it over that whole region. And that's one thing that I think is, I mean, one of our biggest criticisms of that method is you're also making the assumption that within administrative divisions are determined by the number of people within them. So the larger the administrative division, the more rural it is. And so you're making this assumption that distance traveled within Nairobi is the same as, like, or within New York City is the same as within Montana. And that might not be true in this particular outcome.
Thanks.
Yeah.
Any other questions?
Oh, I thought I saw a hand raised, but maybe it was a bye.
Then I think with that, we'll say thank you yet again, Jessica, for a really interesting and informative talk. And thanks so much for joining us, even though it's so bright and early.
Yeah, the sun came up so I'm ready to go now.
And thank you everyone for joining us, and we'll see you at our next talks.
Thank you, Daphne.